In section 7.3 and 7.4, we'll be talking about various formulas involving polygons. With these formulas, it's important to realize that these have to do with convex polygons. And if you remember what convex polygons are, they are polygons where all interior angles are less than 180 degrees. Therefore, I could draw a pentagon, and you'll notice that all the angles are less than 180. Example that would not be is something like this. Oops, that's a straight line, pretend. And this one isn't because you can see right here and right here, both of those angles have more than 180 degrees, so this is not a convex polygon. The first theorem we'll be talking about is theorem 55. The sum, denoted with SI, of the measure of the angles of a polygon with n sides is given by the formula. S subscript I equals the quantity n minus 2 times 180. S subscript I refers to the sum of the interior angles, where n then refers to the number of sides. The next theorem in this section is theorem 56. If one exterior angle is taken at each vertex, the sum of the exterior is equal to 360 degrees. So let's go with our pentagon again. If I have a pentagon and I extend each of the sides going in the same direction, the exterior angle of those, so angle 1, 2, 3, 4, 5, those will always equal 360. It doesn't matter the number of sides. This happens for all polygons. You can very much see this in a rectangle. If I extend each one of the sides, we know that rectangle has 90 degrees. This is 90, this is 90, and so forth. 4 90-degree angles will equal 360. Again, if you have any number of sided convex polygon, the sum of the exterior will always be 360. The same cannot be said, though, with the interior. So that needs to be distinguished. We're going to theorem 57 now. The number of D diagonals that can be drawn in a polygon of n sides is given by the formula. Again, D is your diagonals, n is the number of sides. So the number of diagonals equals the number of sides times the quantity n minus 3, all divided by 2. We have just a few examples using these formulas. The first one is to find the number of diagonals in a pentagon. Now, you could always draw a pentagon and then draw each one to the opposite corner. So 1, 2, 3, 4, 5. So you can always do that where diagonals would be 5. But again, that kind of defeats the purpose. And if you had something with 20 sides, 30 sides, or even higher, that would take quite a while, and you would sometimes get a little confused as to drawing it. So the best, again, is to use our diagonal formula. So we're going to take D equals the number of sides, which is 5, times the number of sides minus 3. Divide that by 2. You get 5 times 2 over 2. The 5's cancel out. And you'll see it's the same as what we got as if we were drawing it. A second example is to name the polygon the sum of whose angle measures is 900 degrees. Again, remember, the exterior will always be 360, but the interior is different. So we know that the measure is 900, so that's our sum of our interior. And we can calculate this by the number of sides minus 2 times 180. So n minus 2 times 180. If we divide by 180, we get 5. We add 2, and we get 7. Now, although this is a 7-sided figure, it says to name the polygon. A 7-sided figure is called a heptagon. It's also important to not only know the formulas for these chapters, but to also know the names of the polygons. And those names of those polygons are listed on page 307 if you forgot some of those names. Again, you'll need to know that in your test, so you need to make sure you know the names so you know how many sides it refers to. And finally, our last example. It says, find the sum of the measure of the interior angles of a nonagon. Again, we need to know how many sides are in a nonagon. And like its name suggests, non meaning 9, we can use the, sorry about that, we can use the number of sides and the interior measurement. Calculate 9 minus 2 times the quantity 180. So 7 times 180 degrees. And in a nonagon, the measure of the interior, the sum of all the interior angles, is 1,260.